Hi, I'm Joe Conway from Crunchy Data. I'm going to do a talk on text search and pattern matching in Postgres. So the point of this thing is that there's a lot of different methods that you can use, and you're going to get different speed characteristics out of the different methods. So what you want to do, generally speaking, you'll see that in some of the examples at the end, but generally speaking, what you're going to want to probably do is use the simplest method that satisfies your need, because that's probably going to be the fastest method, certainly going to be the easiest. And in some cases, you might need to combine more than one method depending on what exactly you're trying to do. So I'm going to go over just a quick summary of the methods that I'm going to cover. I'm going to do a kind of a high-level overview of each of those methods, and then I'm going to go through some example use cases. But a few caveats. I'm going to cover full text search at a very high level. We could probably do a full day on full text search with all the things that you could do with it. I'm not going to try and do that today. And even some of the other methods, especially things like regex, you could spend a full day trying to do a course, a class on how to do regex efficiently. I'm not going to try and do that. The other thing is that a lot of the things I'm going to talk about today have to do with how do I not only do a pattern match, but how do I do it quickly and get Postgres to use an index. And a big consideration, at least one that I've run into over and over again in my career, has been that when you're doing pattern matching, you often want to do case-insensitive pattern matching. And that becomes a little tricky to get Postgres to use an index. There is an extension for Postgres called CI text, which is case-insensitive text. And if you install that, then basically everything you do against that data type is going to be case-insensitive to begin with. That can solve some of these problems, but I'm not really going to address that data type in this talk. But it's something that you can at least keep in the back of your mind as potentially another solution for the case-insensitive. So these are the methods I'm going to cover. In standard pattern matching, everyone probably is well familiar with like. There's also something called similar to, and then there's POSIX style regular expressions, which you may or may not be familiar with in Postgres. There's some extensions that in Postgres, fuzzy string match allows you to do fuzzy matching, as it's called, using soundex, Metaphone, double Metaphone, and something called Levenstein. And then there's trigram matching, TRGM. I always have a hard time saying that 10 times fast, which you'll see is useful not only for the fuzzy matching, but it's also useful for some of the other tools it gives us that allow us to use indexes. And then finally, I'll cover full text search. So a note, I don't know how many people here are familiar enough with how to create an extension in Postgres, but for the extensions that we're going to use, this is the syntax: create extension PGTRGM, create extension fuzzy string match. Those extensions are probably going to be available on your system, but how they get there sort of depends on how you installed Postgres. So if you've installed Postgres from, say, RPMs, then there's probably a PostgreSQL-contrib. At least that's what it used to be called on Red Hat variants. Not really sure. Does anyone know if it's still called that today? Okay. Or if you get your RPMs from like the Postgres development group site, it'll be the same thing. On Debian's, Debs, it's called something similar. If you install Postgres yourself from source, you're going to have to go into the contrib directory and compile and install those extensions yourself before this syntax is going to work. In terms of the examples in this presentation, it's all going to be based on this one table. It's called messages. Magnus, who's in the back of the room, might recognize this. But this table is basically holding email data. It's got a from column, a to column, a subject, the full body text of the email, and then something we're going to hear about later, this FTI column, which is a type tsvector. That's going to facilitate the full text indexing. This table contains all of the emails from the Postgres list for like the last 15 years or something like that, and it contains about just over 1 million messages. So that's going to be the basis of all the examples. I think it's about 80 somewhere around 85 or so gigabytes of data. So it's not huge, but it's not, you know, a toy database either. I guess it depends on your definition of toy. But. So we'll start with just standard like syntax. Like is an expression that's going to return true that if the string matches the pattern. And typically the string that you're matching against the pattern is going to come from some relation in your from clause. And the like expression is going to be used in your where clause to filter the rows. Like itself is case sensitive. I like is another variant which is built into the grammar, which is case insensitive. There's also these operators. So you can say string like pattern, and then there's this optional escape clause that we'll go into in a minute. Or you can use the double tilde. I like has a similar operator with double tilde and an asterisk. And then if you want to do case insensitive, this is what you'll often see is you'll take a lower function on the string and you're compare it to some pattern, which hopefully you've also lowercased. If you need to negate a like, you're just going to use the not keyword, or you can use the appropriate operator. So you can say string not like, or you can put the exclamation point in front. String not I like, same thing. Or you can basically just, because this thing is returning a Boolean, you can just negate the whole expression by putting a not out in front. The pattern obviously can contain wildcard characters. An underscore matches any single character. Percent matches 0 or more characters. If you don't have any wildcards, then this acts like an equals. I think I've had someone point out to me before that it's not semantically exactly the same thing as an equals, but for most intents and purposes, that's what it will do for you. If you need to match the literal wildcard characters, they have to be escaped. And the escape character by default is the backslash, but you can change that with the escape clause that we were looking at just a minute ago. And if you need to match the literal escape character, then you have to double that one up. So now a little side note about index op classes. How many people are familiar with what index op classes are and why you would want to use them? Not too many, actually. Okay. So there's these three built-in pattern ops that are used if you're doing an anchored pattern. So you have a pattern and then a percent sign, and you're not in a locale that's a C locale. Indexes will not, B-tree indexes will not get used, the normal B-tree index. So you need to build the index with these special pattern ops in order to be able to use an index on that kind of an anchored query if you're using something other than the C locale, which now these days virtually everyone is using UTF-8. If you're not using UTF-8, you're probably using some other multi-byte encoding. So in those cases, you'll see that the indexes won't get used for these kind of anchored patterns. You should also probably create a normal index on the same column, because if you want to do any kind of less than equal to type queries, the normal index will kick in for those. But this does not work for ILike or the equivalent operator. And in that case, you're going to probably end up with something like an expression index over lower on the column, or trigram. So here's an example of why you might want to change the escape character. In this case, I've changed the default escape character to a pound sign, and that's because my string has these embedded backslashes. It's got embedded underscore and percent, and I'm trying to match that against the pattern. So in this pattern, what I've done is I don't have to escape the backslashes because they're no longer the escape character. And I'm using the new escape character to escape the underscore and the percent and the underscore. Okay, so now on to similar to. How many people here knew that Postgres supported similar to? A few. So similar to is kind of halfway between a like and a regex. It's sort of regex light. It uses a special SQL definition, which is an extension to the normal like. But it looks much the same. String similar to pattern, with an escape clause or not similar to pattern with an escape clause. So it works the same way, but it also supports these extra meta characters, which are really stolen from regular expressions. You can use a pipe symbol to say, I want one of these two alternatives. You can use an asterisk to say repetition of 0 or more times. A plus is repetition of 1 or more time, so that'll require at least 1. Question mark is 0 or 1. You can say I want exactly m times, or you can say greater than, greater than m times, or between m and n times. And you can use parentheses for grouping these operations so that you can get it correct. So let's see some examples of this. Here, this one operates exactly like a normal like. I'm saying A, B, C, D, E, F, similar to A, B, C with a %. That's going to evaluate to true just like a like would. In this case, I'm saying I want either a capital C or a lowercase c in that third position. So that will also evaluate to true. Here I'm saying I want the letter C to repeat 4 times, and it only repeats 3. So this one's actually going to come out false. But this one I've said 3, so it'll come out true. In this case, I've said these two positions can match any character, and that also comes out true. Any questions with that? So regular expressions, Postgres supports full POSIX style regular expressions, if I can say that 10 times fast. The difference here is that the regular expression is going to match anywhere in the string unless you explicitly anchor it. So if you're familiar with regular expressions, you can normally anchor the beginning and the end of the regular expression. If you want what you're matching here to match the exact string, that's what you're going to have to do. Otherwise, it's going to match anywhere within the string. And this uses operator just a single tilde or a single tilde with an asterisk, which is going to be a case-insensitive version. And again, the trick that we'll see later is to figure out how to get these things, how to get this one especially to use an index. If you put the exclamation point in front, that's the same as saying not. So, as I mentioned before, regular expressions is, you could probably take a PhD on how to write regular expressions. They can get pretty complicated, so I'm not going to try and go into all that. But there is a section on it that covers it in a bit more detail. I've given you a link here in the presentation. These presentations will all go up, so you can look at this later on your own leisure. But in this case, so I'm saying AB and then a lowercase or an uppercase c plus any number of characters with a non-greedy match, and then one or more z's, D, E, F, and then another wildcard effectively is going to match that thing, and that is true. In this one, I'm doing I'm anchoring it to the beginning and the end, and I'm saying it starts with AB, it ends with BC, and it's got any characters in between, so that's also true. This one just starting with AB, so that's going to be true. This one I'm using now case-insensitive match, and I'm saying ABC anywhere in the string, which is true. And then this one I'm saying it starts with ABC, and that's where it ends. And that obviously is not going to match. So this comes out false. Any questions about that? So if you do this with a regular expression, so I'm doing select date, just any field basically, from the messages table where my body text matches this multi-transact. If you hang out on the Postgres lists at all, you've probably seen a slew of messages over the last couple of years about multi-transact. So I've got that baked into a bunch of my examples. That's going to take 27 seconds and not use an index. It's doing a sequential scan. So the solution to that is actually to build this trigram index. This is sort of jumping the gun a little bit because I haven't gotten to the trigram extension yet, but if I create this index on my table using gin and using this special gin trigram ops that comes with trigram, Now when I rerun this query, you'll see it'll do an index scan, and it takes a little bit less than 200 milliseconds. So instead of 26 seconds, 200 milliseconds. It's pretty good. You can also try, Trigram also comes with a gist index, but the difference is that a gin index sort of disassembles the thing and finds all the pointers in the document to any record, right? But gist tries to index the actual field, and in Postgres, whatever's being indexed has to fit on a page. So in this case, because those messages were large, I couldn't index it with gist. For smaller columns, you could get away with that, and you'll see examples of that. In some cases, gist actually outperforms gin. In some cases, gin outperforms gist. And just for fun, again, jumping the gun a little bit, but if we compare what would happen with a full text search, if I did that exact same query effectively using that full text index column, looking for the multi-transact in the body, that's also going to use an index as long as the appropriate index has been built. That comes back in 22 milliseconds. So it's a good bit faster. All right, so now I'm going to go into the fuzzy search methods. Any questions about anything up to now? Okay, so the first one, soundx. Soundx basically takes a string, gives you back a 4-character code. There's also this kind of oddly named function that comes with it called difference. What it actually does is it takes 2 strings, converts them both, and then tells you how many positions match. So it's kind of backwards from what you would think. Difference of 0 means there's no matching positions, and a difference of 4 means they all match. So that's a little bit strange, but soundx was generally designed to find similarity in English-speaking language names. So that's what it works best for, it tends to. It's part of this fuzzy string match expression. If you do soundx of the name Joseph, and here's a Joseph spelled phonetically, and here again is the difference, you'll see that they actually both produce the same result, and the difference ends up being 4, meaning there's no differences. Levenshtein is an algorithm that calculates the distance between 2 strings, and it does that based on character position. So number of characters that match in the same position basically don't count, and positions that don't match do count. This is limited to, it's a case-sensitive operation, and it's limited to 255 byte strings. So again, if I use that same string, Joseph and Joseph, because it doesn't match in this 5th position, that's 1, and because this one only doesn't even have a 6th position, that's a 2. John and Joan are going to be just 1 different, and foo and foo, obviously, there's no difference. So you can start to think about how you can use these things for figuring out how close you want the strings to be before you declare that they match. Metaphone also creates a code similar to soundx, but you get to specify how long the output code's going to be. It's insensitive, case insensitive to begin with. It's also limited to 255 bytes. And you use this max output length to set the length of the output code that you want. So you can take Metaphone of extensive and exhaustive using 6-character output, and the same 2 words with different casing with 3-character output, and you'll see that in that first case, they actually don't match. But if I boil it down to the 3-character output, it declares them a match. So you can imagine using either, tweaking the length of the output string to figure out how close you want these things to match, or you could also combine methods and use something like Levenshtein over Metaphone to say how close do these output strings have to be. There's another one called double Metaphone. That actually comes with 2 different algorithms for calculating the output string. The code in this case is always going to be 4 characters. Those two algorithms can produce different results, particularly for non-English names. This one is also case insensitive, but there's no length limit, or effectively whatever the length limit in Postgres, which is 1 gigabyte in size. So those same strings, extensive and exhaustive, you can see they come up with slightly different codes. And if I take Magnus and compute his name the two different ways, you'll see it also gives me a different code. So trigram matching, this is a different extension. This is functions and operators for determining similarity. Basically what it's doing is it's breaking up any given string into groups of 3 characters, and then it's comparing how many groups of 3 characters match between the pattern and the string. Also importantly, as I've kind of alluded to already, that it comes with these special index operator classes that can also be used by like and by ILike. And the comparisons are case insensitive. So in this example, when I'm using this set limit function that comes with it, basically the similarity operator that it provides makes use of a limit to decide what is the cutoff between what is close enough to provide a match and what isn't close enough to provide a match. And that defaults to 0.3. In this case, I've changed it specifically to 0.6. And then in this query, I'm going to calculate the similarity that it produces using the similarity function provided by Trigram. I'm using the input of the from in my messages table. And I'm using this kind of phonetically spelled version of my name and email address to show you what the similarity it actually calculates to be. And then I'm doing essentially the same operation here to filter the rows using the operator that's provided by it. And you can see when it runs, these things are all above the 0.6 similarity. That's why they are the only ones that came out. But the interesting thing is using this kind of phonetic spelling, it even grabs an email address that I had about 15 years ago that no longer exists because it was close enough of a match. Okay, now we're down to full text search. Full text search is going to be used if you've got complex criteria. It's superior to other methods in a lot of cases because not only can it be faster for large documents, but also because it has special linguistic support. It'll do stemming. It'll remove stop words. It provides some functions for doing ranking and for doing highlighting. And it does come with operators for doing flexible indexing. But as I said, this is a very complex topic. I've given you kind of some links here to some of the main pages in the Postgres documentation. You could spend quite a bit of time just reading through that and understanding it. Usually when you're using full text search, you're going to want to pre-process your strings and produce this tsvector data type so that you can query against it because that pre-processing is expensive. So the way that's typically done is you create a trigger. So in this case, I'm creating a function that I'm going to use as my trigger function, and it's going to assign the value whenever I do an insert or update on this table. It's going to change this value of the FTI column to be a concatenation of a weighted tsvector over the subject and a weighted tsvector over the body. And I'll get into in a moment what that weighting does. But that produces a tsvector that I can search against later. So I create the trigger using that function, and then the other important thing is I want to create this index on that column using gin. And it'll make use of the special functionality. There's just in gin index support for full text indexing. But I'm going to want to have that index in order to make these queries fast. The weighting. There's an array basically that allows you to specify a weight to each of 4 categories. There's D, C, B, and A. By default, they're these values. So the A weight is 1, whereas the D weight is 0.1. What that means is if when you start looking at the relevancy ranking, something that is A weighted is going to be counted 10 times as strongly as something that's D weighted. So in the example that I showed, I've got the subject A weighted and the body text D weighted. And the reason is if I'm searching on some words and that word is in the subject, presumably because the subject is supposed to be sort of a synopsis of what's in the body, if it's in the subject, that's important, more important than if it's in some large body of text. Another analogous situation would be like an article where you've got the entire text of the article, you've got an abstract of the article, you've got a title of the article, and you've got an author, maybe. So you could weight each of those things, and if someone was searching on the author specifically, then you would want that to be weighted pretty high. If they find the word that they're looking for in the title, you would want that to be high, whereas the one word somewhere buried deep in the document may not be quite as important. When you create a tsvector, basically what happens is that your document gets parsed into tokens. There's standard parser support that comes along with Postgres for that, but you can create custom parsers. And those tokens are then turned into lexemes. And what that process means is the word gets stemmed, stop words get eliminated. There's also some prefixing and suffixing. Suffixes can get removed. And also case folding happens. Now the other half of this is what am I using for the pattern? And the pattern is always going to be a tsquery. The tsquery is going to be a combination of lexemes again, which are combined with Boolean operators. So you can say and or not. The not is going to bind most tightly, so it's going to bind tightly to whatever it is next to. And is going to bind more tightly than or. But of course you can use parentheses, and I would recommend you do that. You can completely depend on this priority when you write your tsquery, but it's not going to be as readable if you don't use parentheses to make it clear where you want your groupings to be. You can also label with an asterisk, which means you want to do prefix matching, and you can also define weight labels, and we'll see that in a minute. When you write a tsquery, you're going to use either this function toTsquery, which will take the string that you provide and it'll normalize the tokens into lexemes and it'll discard stop words. You can also cast it to a tsquery, but in that case, the tokens are not normalized, meaning stop words are not removed, it won't be lowercased, they'll just be taken at face value, and it doesn't support weight labels. So if you look at this example here, I'm saying toTsquery hello in my subject, and the word the in my subject, or the word writing in my body. That's using the toTsquery. And then here's the exact same string, but I'm just casting it. And if you look at the result here, you'll see that when I use the toTsquery, I retained my weights. The word the, because it's a stop word, just got eliminated entirely. And in this case, the word the is still there because I didn't process it the same way. I didn't normalize the tokens. And I also lost my weights. In this second part of it, I'm using the word Postgres : asterisk, which means I want to use Postgres as a prefix. I want to find anything that's going to match Postgres plus. And I do that in both methods, and you'll see in this case, Postgres got stemmed, and I retained my prefixing. In this case, Postgres did not get stemmed. It just got left, it got taken at face value, but I still am considering that to be a prefix. And there's one more way that you can do tsqueries, and that's plain to tsquery. This one is a little bit strange in my opinion. I'm not quite sure why there was the need for it. Maybe it was just historical for what was there in the contrib before this got folded into the back end. But in this case, the text will get parsed and normalized. But any operators you have in there are going to get ignored, and basically the AND operator just gets slammed in between all of your resulting lexemes. So you should really use simple strings only. It doesn't support Boolean operators. It doesn't support weight labels. It doesn't support prefix matching. So if I take that same query I was looking at before, the same two, and look at what the result of using plain to tsquery, you'll notice that I get hello, but I also get the B that I was trying to use as a weight label, as a search term, and I get another B. The word the is gone because I did normalize, so I removed the stop word, but everything got combined with ands. And in the case of my attempt to use a prefix, that just got stripped off entirely. So I think the bottom line here is that these three different methods produce three different results. So if you're going to use full text indexing, make sure you understand which method you're using or your developers are using, and you really understand what query you're writing, because they are, the three methods on the exact same query strings produce subtly different results that are getting matched against. In full text search, the match operators is at. This is going to return true if the tsvector matches the tsquery. And either one, it doesn't matter which one is on which side of the operator. So in this case, I'm just doing, this part in the target list was just to make sure I wasn't showing email addresses for other folks than myself, because I didn't want to aggravate anybody. But I'm matching my tsvector column using the operator against a query that says I want multi-transact in the subject and the word race and bug in the body of the email. And that comes up with three different hits. Any questions about that? Well, back a few slides when I was talking about the weighting. So those are what are used for the weights. In this case, well, I also, when I set up my trigger function, you'll notice that I use the A weight on everything that came from the subject, and I use the D weight on everything that came from the body text. So by using those weights, I'm saying I want to match the stuff in the subject versus matching anything. Or I want to match the stuff in the body versus matching anything. And that also gets used for the relevance ranking. So that lets me be more specific.
That's because it combined the body and the subject in one FTI column, right?
Right. I could have actually had separate columns for each of those as well. But if I wanted to match, regardless of what I might want to match on a word, whether it's in the subject or in the body, and because of the way I did it, you could do that.
So is it that, if it matches the A category, you add one. If it matches the B, you add one.
If I didn't use the weighting in that particular query, it would just look for that word in either the subject or the body. Because I used the weighting, it would look for it in the subject specifically.
So does it do like sum of A matching A?
When we get to the relevance ranking, it'll actually take that into account. So when I'm doing relevance ranking, I'm trying to say this is the record that matches my query best, right? And that's going to use that relevance ranking to say, all right, if the word I was looking for in the subject matched, that's going to provide a higher relevance value than if the word I was looking for in the body matched. So when I then sort the results, I can get just the ones that match the best. Make sense? Okay, so this is how you do the ranking. There's two functions, tsrank and tsrankcd. Basically, the difference is that the cd function is going to take the proximity of the lexemes into account as well, whereas the normal tsrank ignores the proximity of the lexeme. So you might, if you find a cluster of the words that you're looking for closer together, and that's you think is important to your search, you could use this tsrank CD. One of the things that when you're doing that, you're going to want to return that calculated value if you want to be able to order by it. And you end up needing to use that same tsquery in your filtering clause too. So I find it useful when I'm writing this to use a with clause, basically to do that calculation once and then refer to that query in both places where it's needed. The other feature that's provided is this highlighting. So this TS headline is going to return returns an excerpt of the string that you're matching against with the query terms that are highlighted. And what I'm showing here is that function is actually fairly expensive. So if you were to run that as part of your query against the whole table, it could be kind of slow. What you really want to do is pull out just the records that you're interested in based on whatever your cutoff is going to be for relevancy, and then apply that headline just to those records. So the way I've written this query, I'm basically using that headline in an outer query, and then inside the inner query, I'm doing the filtering of the rows. So I'm just saying I want the most important row that matches this query, and then I'm going to use the headline function on the subject and the body text. And so it gives me basically this HTML bolded output. Okay, so now I'm going to go on to some example use cases. I'm going to start out at the simplest. I just want to do text equals 15, okay. And then I'm going to move down through more complex cases. So I'll do anchored, and then anchored with case sensitivity, case insensitive, and then a reverse anchor, and then a completely unanchored, and then fuzzy, and then another full text search example. So if I'm finding all the rows where the column matches some patterning exactly, that's just basically an equals. Without an index, this query, now in this case I'm running against the from column, not the body text, it has to do a sequential scan, and it's going to take about 500 milliseconds. Now if I build the index on that column, just a standard B-tree index, and I do my equal match, it comes back in 161, plus planning time, call it 400 and something microseconds. So before the examples we were looking at before were like 20 milliseconds, 200 milliseconds. This is coming back in microseconds. That's important to keep in mind as we go through these examples. So now I want to match an anchored pattern. If I use a like operator with a suitable index, that's going to be the best thing. But our normal B-tree index, you can see, I create that index, I run this query using a standard anchored pattern, and I still get a sequential scan, and it takes 500 milliseconds. But when I build the index this way, so on messages using text pattern ops, and I do that same exact query, now I get an index scan, and this thing returns in again, if you add the two, it ends up being a little bit over 600 microseconds. So it's still less than a millisecond. So that's why I said at the very beginning, if all you need to do is this is lightning fast, and it's pretty simple. So now I want to do the same anchored pattern, but I want to do it case insensitive. So I'm going to create an index, an expression index. I'm going to use the function lower over my from column, and I'm also going to say with text pattern ops. And when I write my query, now I have to say lower of that column is like my anchored pattern. And just to be safe, I might have written this as lower over that string, but this is already lowered, so it won't matter. This is going to use an index, and it still returns in just over somewhat less than 800 microseconds. So again, it's still really fast. And now I've got a case-insensitive anchored pattern. Now, you can also do this. Remember I was talking about the Trigram extension. I can use a Trigram gin index. So if I build an index on that column using gin with the gin Trigram ops, and obviously I had to drop, in order to do this example for the slides, I have to drop that other index so it doesn't get used. But it does an index scan. It uses that index that I created. But now if you look at it, I'm up to 93, 94 milliseconds. So this is like a couple of orders of magnitude slower. It's still pretty quick, and it might be fast enough for what you need, but it's nowhere near as fast as using that expression index. And you can also do gist index with ILIKE. Actually, that last one was also with ILIKE in order to get the case insensitivity. Sorry, I missed that. This is going to look exactly the same, except I use the gist Trigram ops. And it's a little bit faster. It's about 54 milliseconds to run. So now what happens if I want to do a reverse anchored case? I want to say wildcard and then pattern. Well, a pretty simple answer is I can actually use an expression index again, except now I'm going to do it on lower over the reverse of the from column. I'm going to write my query where lower reverse of from is like, and I'm going to reverse my pattern. It'll use that index that I created. And this actually ends up returning a little faster than the other ones. It comes back in like 17.5 milliseconds. But again, way slower than those microseconds we were seeing before. I can use, again, the Trigram gin index with ILIKE. And that'll come back in about 89 milliseconds. And I can use the gist index with ILIKE, and it comes back in about 67, 68 milliseconds. Okay, so now what happens when I want to do an unanchored, completely unanchored? How many people have seen their developers write queries like this? Pretty much everyone, right? You see this all the time. And the problem is we're using the standard methods. There's really no way to index that. So if I run that query without an index, it takes 2 seconds. But again, we get Trigram comes to the rescue. I can use Trigram index with ILIKE and get a case-insensitive, completely unanchored use of an index to satisfy this query. So now when I create the index using the Trigram, gin Trigram ops, and I'm searching on wildcard, Conway wildcard, it finds a bunch of rows, it uses the index, it comes back in like 31, 32 milliseconds. So not too bad. And this is, as you saw with the full text indexing, there's a lot of stuff involved in that. So this might be all you need. For shorter strings, it probably performs similarly to full text indexing. I think for longer strings, it probably doesn't. You can also use gist. For some reason, in this case, gist actually loses to gin by quite a bit. And I think the lesson there is if you are going to make use of these gist and gin indexes, there's always discussions on the list. What should I use, gist or gin? I think the most recent guidance on the most recent versions of Postgres is that at least for full text indexing, it used to be that you used gin if you wanted to make your queries fast, but it was slower to update and the index size was larger. Gist was faster for updates and the index size was smaller, but it was a little bit slower. In the most recent versions, I think the guidance has now switched to, for full text indexing, you probably want to use gin all the time because they've managed to shrink the size of the indexes and speed up the inserts and updates enough where there's not much downside to gin. But for all these shorter strings, for this type of application, sometimes gin is faster, sometimes gist is faster. So in your use case, you might want to benchmark it and figure out which one works better. So now we'll do another example on fuzzy string matching. I want to find all the rows where a column matches some pattern, but in some inexact way. In this example, I'm going to use Metaphone, but I might have also used SoundX or Levenstein or the other methods that we talked about already. So if I create this, again, and I'm going to create an expression index on messages using Metaphone over the from column. And now, so when I select from messages where Metaphone of from is equal to Metaphone over this very phonetically strange spelling of my name, you end up getting 108 rows. And again, we're back down into the microseconds range. So these expression indexes actually perform quite well. And finally, one last example using full text search. If I want to use complex multi-word searching and I want relevancy ranking, that's probably going to be what I'm going to want. So if I select date from messages where my tsvector column has the word bug in the subject, deadlock and startup in the body, and it comes back in this case about 13 milliseconds. And that's all I have. Any other questions?
About how much longer would that last query have taken if you tried to get the, results for the header?
If you want to do the highlighting? So how much longer would it take if you wanted to do the highlighting?
You said it took significantly longer. I was asking for
Well, if what you did was you used the highlighting function in the inner query, it gets applied to every row as it's trying to filter it. So it sort of depends on the exact query plan that gets used and how far down that gets pushed. But in the testing that I was doing, if that gets pushed down, it could make the query take a really long time. And if really all you want are the top 10 results, you just don't do that part until the very end. So filter your result set down to the top 10 results, and then in the outer query, apply that, and you won't even notice the difference probably. Yeah?
How does unanchored text search compare to just regular expression search?
How does an unanchored text search? So if we can go back to that regular expression example. So in that regular expression example, it was coming out at 192 milliseconds, but this is a little bit apples and oranges because this particular query I was running against the body text column, which is the big, and the other example with the unanchored that I was showing you before at the end was against the from column, which is just the email addresses, so it's a much shorter column. Honestly, I don't know what the answer to that is, but we could try it over a beer after the talk is done.
Did you talk about making the regular expression versions use index? Is the same process as getting the text ones?
Yeah, in the example here, this is the regular expression version of the query using the, again, the Trigram ops.
Okay.
So in order to make it use the index, you need to install that Trigram extension. But once that's installed, you can create this index and then get it to use it. Anything else? Thank you.